Well, it's time. Welcome back, everyone. We're on our final instructional week for the entire semester, so congratulations on getting to this part. Week number 15 is a good place to be in. Our goal for this week is just to finish up the last topics in section 8.4. Then we're going to move into the final exam review problems. That'll pretty much be our last document that we're going to work out these in this week. We should be able to get through all the problems, but any problem we don't finalize 100%, I'll get fully solved after completing the grading on Friday. Other things going on is that the last homework assignment, section 8.3, is due Thursday. And I have a smattering of extra credit opportunities I want to discuss one by one, but any questions or comments so far? Okay, well, as far as the extra credit goes in the course, there's really two main opportunities and a third kind of a pseudo extra credit opportunity. The first one is relative to your final exam. If you look into your minimum scores amongst exams 1 through 3, if the final exam happens to exceed that minimum score, it will full on replace it when I compute the final course grades. So if you had a lower exam, you really shouldn't be punished for that if you come back strong on the final exam material. It's a way to kind of make up credit on any rough area that might have occurred amongst those exams. The other extra credit opportunity is about removing the pop-up for course evaluations that happens every time you click on the Canvas course page, I think for all of your courses. So the way this extra credit opportunity works is in the syllabus, there's a guarantee already of dropping the lowest 2 homework assignments at the end of the semester. If you do the course evaluation page, get rid of the pop-up when you click on the Canvas course page. Send me a quick email either through the Canvas system or my Gmail account, and I'll drop a total of 3 lowest homework assignments at the end of the semester when doing course grades. That way, if there's a couple assignments that were a little bit rougher, it really shouldn't affect your scores too much after dropping those assignments. Then the final kind of an extra credit opportunity is if you fell behind on any assignment whatsoever, if there's an assignment that's late, check your Canvas grades. Maybe send me an email if you like, that will work out fine. I'll accept any late work for full credit with the final cutoff date. I guess that would be 11:59 p.m. on Thursday, May 7th. So that's the full set of extra credit opportunities. Any questions or comments at the moment? Okay, well, as far as the final exam goes, it's kind of going to be scheduled for the online section, just exactly like we did exams 1 through 3. I sent out a message early on Monday morning, if you're in the online section, to schedule with your preferred campus. For the in-person section, the official time is going to be in the classroom Tuesday, May 5th from 12:30 to 2:30 p.m. And just like we said for all people in the class, out of a sense of fairness, scheduling exams for the online section is open between 4th if you want to take it early, up to the 7th. And that will apply to the in-person section as well. So if a different day just works better, especially if there's, say, an exam conflict, anything like that, just let me know and I'll work with you right away to get an exam sent over to a testing center. And scrolling further down, here's the bottom of the entire Canvas course page. We have a final exam formula sheet. So this is going to be the real last page of the real final exam. This formula sheet is now firm. All the exams have been sent to the testing centers. So anything that's not on the sheet is considered to be material that must be memorized for the final exam. So I first have a rundown of just basic sets of numbers. This one was a particular request and it made sense to have this on here. Set operations. Here we have some definitions of propositions, logical equivalence, tautologies, satisfiable, not satisfiable. After that, we have some quick definitions about predicates, implications. Here, I put in the proof by induction. If it's a proof by strong induction that comes up, again, you just make a modification. 2 base cases, and the way we did our problems was 2 prior inductive hypotheses. Oh, I guess proof by strong induction is on there, so I didn't need to say that. Looks like we have both on this exam. From the number theory section, I put down this information here, properties of modular arithmetic. Next, let's see, we've got information about inverses in the set Zn. Beyond that, I'm not going to ask a lot of chapter 8 questions, but I felt like It deserved a nice amount of real estate because it's the new topics. It makes sense. I have all the definitions of relations along the lines of reflexive, symmetric, transitivity. So that's the full set of notes. There are no notes relative to section 8.4, but that's going to be the extra credit problem, the very last question on the real final exam. So if you choose to ignore the section 8.4 problem, it won't hurt you. But if you study the notes here, I'm going to ask a question highly similar to exactly one problem out of that 8.4 section, and it would be rewarding. Really, it's kind of intersects with dealing with symmetry, reflexivity, and transitivity anyways. So studying the 8.3 material helps with 8.4 in the first place. So that's the last page of the final exam. I have two other sample final exam problems, versions. Version 1 is gigantic because now it's the entire lecture notes. And version 2 is just as large because this is new problem. A parallel universe with different lecture notes. That's what it would be, version 2. So your idea for these is not necessarily that you're going to print one out like 60, 70 pages, solve every single problem. It's more along the lines of if there is one section you feel like you're a little bit weaker at, maybe say it's the quantifier section, or maybe it was proof by strong induction. These documents allow you to target on a section by section basis a good set of practice problems. For something that's more compact, the length of, say, a real exam, which won't be that long as these problems are, it'll be something similar in terms of the difficulty and length of what we're going to do on that sample exam there. But I think that's my full set of comments. We'll reiterate some of them briefly when we come back on our review on Thursday. But any last questions or comments so far? Okay, well, we're going to spend a little bit of time in section 8.4 just to finalize this last section. Then, with the time we have remained today, all of the time on Thursday's review problems there. So let's jump back in where we left off. I threw in this definition, just copy pasted it down for a quick reference. Equivalence relation is just a relation, so a subset of a cross product of a set that happens to be reflexive. So by reflexive, we mean having this property for every element in the set. The element is related to itself. So XX as an ordered pair is in the relationship. It has to be symmetric. So symmetry is going to be this property down here. If AB is in the relationship, if A is related to B, then B is related to A. It's also in the relationship. And transitivity is going to be this one down here. Forgot how much scrolling I have to do to get through these. Even further, transitivity is saying if A is related to B and B is related to C, we can make a jump from A to C, and A must then be related to C. A C as an ordered pair is in that relationship. So we're going to review those three specific properties of relations since they are the big three that forms what we call an equivalence relation. Well, any questions at all, folks, with the recap of definitions? Okay, what's interesting about all this is now back into set theory. We defined partition. We didn't do a lot about it except practice writing down some partitions for finite sets. So let's review this definition and now view it in terms of this theorem, what a relation would say on a partition. So if we have some set S, that's like, say, the set A we've been dealing with in prior problems, and a brand new set X, which is a set of subsets, A1 through AK. K could be exactly 1 or some large finite integer. Suppose that this set X satisfies two properties. The union of all the subsets in X gives us back the original set S. So we have a union condition. And the sets are all disjoint. For AI, AJ, I not equal to J, they are disjoint, but let's review that. That just means AI intersect AJ is the empty set, non-overlapping sets. So we take some set S, we are now partitioning it into discrete sets that are non-overlapping, a finite number. If we can do that, If there's no intersection, if the union is the original set S, then that tells us we have a partition. So this is what a partition would look like. So again, that's kind of just review from material way back in the day on partitions. But now we can define a natural relationship on a partition. So here's the theorem in the same notation as the definition above. Let S be a non-empty set. So here's our set. We're assuming there's something inside of it. X is going to be a set of subsets from S. That happens to be a partition. So it satisfies both properties 1 and 2 simultaneously. Then we can define the relationship R in this way. We'll say AB is in R. Said differently, A is related to B. If and only if there exists some set AI in the partition, some set inside here, such that both elements are in the same set from that partition. So likewise, if we do a really fast example here, if we say through that theorem, AB is in the relationship, and let's do another one. Let's say XY is not in the relationship. The way we can then visualize this is if A is related to B, then there's some set AI, let's say this is the set, such that both A and B are in that same set. AI is somewhere here, or A, and B is somewhere here. So A and B are in the same set in the partition. If XY is not related to each other, if it's not in the relationship, that means they're in different sets. There is no one set you can find such that both X is in this set and Y is in that same exact set. So you could visualize it this way. Here's X, but Y happens to be here, a different set in the partition. So this is what a non-related ordered pair would look like. They're in different sets. This is AI. This one would be, let's just give it a name, AJ. Being related means they came from the same exact set in the partition. So that's a natural relationship that we can define the moment we have a partition. But the next theorem we hinted at gets even better. An equivalence relation defines a partition on its own. This theorem says if you define the relation in this way, it's also automatically an equivalence relation. So this is a kind of theorem that goes forward and backwards in a certain sense. Well, any questions? Visualization of this new type of relationship? Okay, so property, these kind of partitions are nice in a certain sense. Hang on, I just had something tell me my connection is unstable. How can I check that? I guess I could ask Zoom. How's the connection working? Am I lagging?
You're doing okay. You sometimes cut out for a couple seconds, but at least for me, I can interpolate what you were saying.
Okay, glad to hear that. I'll try to pause if I see that warning again. I don't know what's going on with this is on a direct line internet connection here. You know, I had problems last night as well. The whole Zoom client just disappeared. The screen share disappeared and it reappeared again. Maybe this computer's just tired, who knows? But let me know if anything cuts out and I'll recap whatever I just said.
The computer just wants to be done with the semester too.
Yeah. Well, let's see what's going on with these ideas, putting them all together. First, we need one more new definition, so-called equivalence classes. You know, these are probably easier to visualize if we carry this down one more time. So let me take this. Let's visualize equivalence classes this way in terms of partitions. And this is the last set of definitions and theorems, I promise. The major definition is, of course, the equivalence relation. We'll practice it on the next example. But once you have an equivalence relation, it implies a partition. And if you have partitions, the next natural object you'd want to is the equivalence class. So the equivalence class of an element A in a set A is defined to be, well, first let's rewind, sorry. We start with a relation. It's a relation on a set A with the reminder here that it's a subset of A cross A. We're going to assume it's an equivalence relation. So that means this relation is symmetric, it's reflexive and transitive. And then once we have that, we can define the equivalence classes. The equivalence class of any element in the set A is defined this way. It's the set of all elements such that A and B are related. We typically write this with a new notation. Once we have an equivalence class, the equivalence class of A under a relation R is denoted in this way. So we could rewrite this as equivalence class of A under the relation R. If we drop the notation, the subscript R there, be implied somehow in the problem. We would all have to know exactly what it is. But I'll use this notation strictly since it's brand new notation, conceivably. So the A that goes here is the same element here, and this just generates a set. It's a set of all the other elements B that happen to be related to the element A in the very first place. So if we visualize that out, let's put down a couple elements. Let's call this A, B, C, D. And let me zoom in a little bit further. Let me call this one X, Y, P, Q, just because I don't have a lot of space to put elements on that one. Let's call this 1, 2, 3, and 4. So we have a partition here. If we say that this partition came from the relation R, then that's kind of jumping the gun a little bit, but the theorem says that's absolutely allowed to do. If R is an equivalence relation on a set A, then the set X, this is a set X of all equivalence classes, partitions the set A. So if we have a partition, we have an equivalence relation, we can put down equivalence classes. And going backwards, if you have an equivalence relation, write down all of your equivalence classes. This theorem says you have now formed a partition of the underlying set A itself. So that's in the way the logic goes forwards and backwards. So if we look into this partition right here, the equivalence classes would be the following. There are 5 equivalence classes corresponding to the 5 partitions. Those numbers will always be exactly equal. The equivalence classes, some of them are basic. For example, the equivalence class of Q under this relation R that we've defined just by points and partitions contains nothing but Q. The equivalence class of the relationship A under R, however, it contains all the elements related to A. But keep in mind, this is an equivalence relation as well. So you can say A is related to A, it's reflexive. So A is inside here, so is B, C, and D. So all the elements here form the second partition. A is just the representative, but you can change that out. So you could rewrite this as being equal to bracket B. That could be your representative of the equivalence class or any other one of these elements. Sometimes there's a natural element to pick, a canonical one, but there's no strict requirement here in our definition that there must be a unique way to represent the equivalence classes. There's non-uniqueness in its representation by its nature of the definition. We'll fill out the rest, but any questions so far? Okay, as far as the rest goes, here the sets get a little bit smaller. The next partition includes X's and Y's. If I write out this way, X is the representative. X is in that set because it's related to itself. And it must also be related to Y. Then moving on to that one, this is another simple set. The equivalence class contained the element P under the relation R. is the set that contains just P. And then last one, pretty similar to the prior one to the left, is equivalence class containing one under the relation R is 1, 2, 3, 4. So those are all the equivalence classes. My set A is now defined to be the set that contains A, B, C, D, X, Y, P, Q, and 1 through 4. Because if this is a true partition, it has all elements of that set. Take the union of all equivalence classes, in other words, you get back the original set A, or S rather in this definition. So that's what equivalence classes are. Our job is to just practice working with the equivalence class in a couple fast scenarios. But at this point, we're pseudo reviewing for
just
the
had
final
a
exam
quick
anyways. Sorry,
interject.
go ahead.
So you said that an inner or a union of all of those classes is the original set S, and then would it follow that, or not necessarily, anyway, would it also be that the intersection of all of those classes comes out with the null set?
Oh yeah, absolutely, definitely. Since this is a true partition, let's write that out as well. We have that for any equivalence class, it goes A, Q, A, X, P, 1, but let's maybe write out generically. Any equivalence class phi intersecting any other equivalence class psi, Greek letters because I'm running out of symbols, is equal to the empty set for any phi not equal to psi in the set A, which contains P, Q, X, Y, A, B, C, D, forgot a comma there, 1, 2, 3, and 4. So absolutely, the union of all equivalence classes returns the original set A. Because it's a true partition, these pairwise intersections, always the null set exactly as you said, for any pair of representatives that are not equal. If you intersect with, say, A with A, you would just get the entire set A back. But other questions at the moment? Okay, well, there's lots to visualize when it comes to equivalence relations, whether it's dealing with, say, writing down the sets as an exhaustive list of all of its elements, writing down the directed graphs like we did in section 8.3, or visualizing partitions if they're equivalence relations like in this section. That's a really humongous topic. So what we're going to do now is kind of loop back into reviewing other topics in the semester. Our first relation directly applying these ideas is going to be congruence, mod 7. And then our next relation is going to be logical equivalence. This one will be an interesting one because our set is going to be all propositions that you can form with two variables. And that was a real relation. Same logical equivalence we did in the prior chapter 3. We just didn't have the ability to call it a relationship. We didn't define any of that ideas so far. So logical equivalence is an equivalence relation. So is congruence mod 7. And you might have noticed this is kind of a theme. Things that are really nice equivalence relations are written in a way that practically looks like an equal sign, because that's what we're really doing with any equivalence relation. We're generalizing the notion of equality, and we're saying anything inside this equivalence class is considered equal under the relationship. So now let's focus on congruence mod 7. We'll write down all the equivalence classes. But to make all this work, we have to do a review problem. There's going to be no sense to what the equivalence classes are. These are undefined unless we have a true equivalence relation. So that's our first stop on this one. Prove congruence mod 7 is an actual equivalence relation. The set A in our definitions above is now the set Z of all integers. But it's a fast proof, kind of like the first example when we're looking into connected computers on a network. We just really have to go down the motions. For the equivalence relation, the first check is reflexivity. And for the review on reflexivity, the way we work on this is we start with a generic element in the set Z, just one. We'll say let A be in the set Z. Now, if we pull up the properties, it's kind of depend on how you want to write down the notation. You might have noticed that our author has focused very, very carefully on bracket notation and set membership notation as well, as a reminder that the relationship is a set itself. So if you decide to match up that property, that would be just fine. But way back in section 8.2, our author has also said, although he has hardly used this anywhere in the reading, that X related to X can also be written this way, XRX. So if you decide to go in that way, that would be appropriate as well. So this would be a problem where you get to pick your notation. For me personally, as far as the notes go, because we've practiced one notation more than the others, I think it makes sense to stick to this same notation. That way it won't feel like we're doing something totally different. So this is how I probably would begin this problem, keeping all the sections the same, all the work we've done to date in reading pretty similar. We'll say, next, consider A congruent mod 7 to A. We need to check if this is true or false, but this would mean A mod 7 is equal to A mod 7 using the definitions of congruence mod K from section 7.2. And this equation is absolutely true. So whatever the remainder is after dividing A by 7, you get the same remainder on the right-hand side. So this is really just reflexivity of ordinary quality of numbers. So then if you follow this notation, you would say this means A is an element of R, but the other thing that's confusing about this problem is we never wrote down the symbol R. That's R, the relation, congruence mod 7. So we would write it this way. AA is in the set congruence mod 7. If you didn't use that notation, you would just say, then A congruent to A is true. So you might end it up differently by saying, i.e., A congruent to A mod 7 is true. Really, we're saying the same exact thing, whether we're saying the ordered pair is in the set for the relationship, or the relationship in the middle, as it was introduced in section 8.2, it's really all the same kind of information. So again, totally up to you how you would like to indicate that. I'll keep it in this notation just as a better, stricter review, so we can feel like we're doing the same things from the last section. But any questions or comments at all, folks, on reflexivity? Okay, well, we're 33% of the way done. We move next, or maybe let's make a conclusion. This shows congruence mod 7 is reflexive. So that part's done. Equivalence relations are a 3-part proof, so now we just move on to the next thing, symmetry. There were 3 symmetry relations, and they're tricky to track through, especially looking at all 3 definitions simultaneously for the very first time. But the good news for us is that we're looking at just one property. So I'm going to highlight to here. That's all we need for symmetry. This time, for the review of this property, we need 2 elements. We need an element A, an element B, both from the set Z. So let's begin by saying, let A in Z and B B and Z. So we have two arbitrary ordinary integers. Next, we have an implication. If A is related to B, we need to justify that B is related to A. And again, these go just as fast. Most of the stuff we're doing here is just tracking the definition and then doing a bunch of writing that looks about like that, saying, well, that's got to be equal. Much the same idea as what we're doing here. First, we have to make what our assumption is. We're doing an implication, we'll always say, assume AB is an element of the relation R. Then we say next, this means A is congruent to B mod 7. But again, these are verbatim saying the same exact things. We just put the relationship in the middle, much like this notation we were mentioning in the prior thing I deleted there. But once we have that on paper, we can say the definition of congruence mod 7 implies A mod 7 equals B mod 7. We need to turn that around, but we're using the same idea that we used here. We knew that equation's true because ordinary equality of real numbers is reflexive. X is equal to X for any real number, and X mod 7, same property. Equality is also symmetric. You can swap the left-hand side, the right-hand side. The equation's still true if it started true. So if A mod 7 is equal to B mod 7, again, it's not the craziest step. The hard work here is just carefully tracking what the definition is trying to say. We switch this around to B mod 7 equals A mod 7. If B mod 7 is equal to A mod 7, notice we have just a huge train track of implications. Logical implications are transitive. So starting from here, connecting through means one far left side connects to this far right side. This implies B is congruent mod 7 to A. But that's what we want to show. If we can put B on the left-hand side, A on the right-hand side, it means the relationship swaps. That's our way of thinking about symmetry. So that's our conclusion. Therefore, BA is an, I want to say R, but let me backtrack. I'm just so used to saying R, I think. The actual relationship R, let me say it up here on paper. R is congruence mod 7. That's kind of painful to the eyes to see equalities in juxtaposition with another triple equality stack. I forgot to say it here as well. This time the relationship R is defined in this way. We never put R on paper, so that's probably the best way to make the conclusion. Therefore, BA, we swap the order. It's related to each other in congruence mod 7. Congruence mod 7 is symmetric. Now all we have to do is turn to transitivity. But the theme continues. We'll use transitivity of the equality of ordinary real numbers to show that there is also transitivity for congruence mod 7 as well. So that's our next stop. Any last questions at all, folks, with the symmetry side? Okay, so finally for transitivity, we now take this property all the way here on the bottom of the notes. It feels like a lot is going on with transitivity, but really it's not too different from the other things we've been doing. Take whatever the conditions are. There is a universal quantifier. We need any A, B, C in the set A, which is the set Z of integers in our context. So that's where we start. Really just tracking the definition verbatim, left to right. Let A, B, C be an element of Z. So now that's any real number A, B, C. Hang on, I forgot the C. whatsoever. There we go. The element of got me kind of mixed up with the actually element Z. So that's this first part. Now the implication we're tracking has this for the hypothesis and just that for the conclusion. So that means we need to assume two relationships hold immediately under congruence mod 7. So let's say that next. Assume AB is in that relationship and B is related to C under congruence mod 7, or an element of the relationship. So that takes care of the first two parts here. We need to make that conclusion, but we have to justify why it holds. So we just go back. Here, another way to rephrase that is, this means A congruent to 7, excuse me, A is congruent to B mod 7 is the right way to say that, which then implies A mod 7 equals B mod 7. Also, we swap over to this one, we can just rewrite B is equivalent, or better to say congruent, to C mod 7, which implies B mod 7 equals C mod 7. Therefore, now we make the jump. We're using properties of real numbers again when we make this jump. All we're going to say is, if that equation there is true, or that's the far left-hand side of a true equation, then we take the right-hand side, but the right-hand side gives us a second true equation related to this far right-hand side. Then this is just basic algebra. We can make the jump. These two have to connect because that's ordinary equality, which is transitive. So we can say as a big statement, therefore, A mod 7 equals C mod 7. This is equality as real numbers, which implies A is congruent to C mod 7. We switch back now to the bracket set membership relation. This implies, or notation rather, this implies the ordered pair AC is an element of the relation, which is a set, congruence mod 7. So we verified three properties, which means we have one big overall conclusion. We can now say, therefore, congruence mod 7 is an equivalence relation on Z. So we've done it, folks. That was our big target for this particular problem. Reviewed three properties from section 8.2. And this was our overall goal, to get to that equivalence relation. But that means we've done something in particular to Z under this relationship, congruence mod 7, or congruence mod anything, mod 2, mod 16, any kind of modulus congruence we have right here. Z is now partitioned, much like this. There are now equivalence classes that Z is related to. And so that's what the next part of the problem is all about. Now that we have an equivalence relation, the next natural question is, what are the equivalence classes on Z? We're going to compute them, see what they are, and see if we can convince ourselves that we have really partitioned Z, that there is no intersection whatsoever in any of those equivalence classes. Their total union gives back Z itself. Well, any questions at all, folks, with the next phase? Okay, this is where something like Z7 starts to have a true algebraic structure. We would sometimes call this a finite field, just like the set of real numbers is an infinite field. has the same properties. There is a unit 1, that's going to be an equivalence class. Every equivalence class inside of here, we're going to find them all, are invertible if they're non-zero, because 7 is prime. And so all of our properties of algebra that we know and love that we use on the set of real numbers, now that we have an equivalence relation and a new notion of what equality even is, they could be defined here. And so it's the first big example in algebra of a finite field, much like R being an uncountably infinite field of numbers. So that's kind of the big punchline to what the equivalence classes are doing, providing us a way to get a new algebraic structure. So let's write them all out. Set of all equivalence classes for the relationship congruence mod 7. First way you'd probably want to start this out is write down as a review topic that Z7, in our prior notation, this was in section, say, 7.4, would be written 0, 1, 2, 3, 4, 5, 6. So this was old notation in section 7.4. And it was kind of loose notation. We could have written this in a much, much better way. And that's essentially what we're about to do right here. We start off with the equivalence class 0 under the relationship congruence mod 7. Notice it's in the element of Z7, and the proper way to write that is actually with the bracket. The bracket probably wouldn't have congruence mod 7 on it because it's implied. That's the relationship when you write out Z7. Let's also maybe put down just a quick look at the definition. When we say equivalence class of A, for any relationship R, we mean the set of all elements B in A. The set A is playing the role of the set Z up here, such that BA, or you could say AB because this is symmetric. I think we went to BA is an element of R. Let me double check that's in the right order. Oh, no, they swapped it. Again, it's immaterial because symmetry allows you to swap them, but let's keep them in the same order just so it doesn't look as distracting. So that's what the equivalence class definitions give us. We have a whole new set. We have a particular relationship R. So now let's write this out as a set. I'm not going to write the most precise set. I'm going to write out as if you're writing out the set of integers Z, which might be 3, 4, or 0, 1, 2, 3, dot, 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 to say, and so on, -1, -2, -3, and so on. So in kind of a loose way, just so we can see the patterns a little bit better, I'd probably start 0. For any equivalence class whatsoever, the element that's representing that equivalence class is automatically inside that set. So we can start with 0. And now, what else is congruent to 0 mod 7 is the question. Well, the next entry should be 7, right? Because 7 is congruent to 0 mod 7. Or in other words, 7 mod 7 is back to 0. So what we're saying here now, when we threw in that 7, 0, 7 is in R, since 0 is congruent to 7 in this way. But if 0, 7 is in R, that's the 7 that we threw in, the new B element. Let's maybe match the color coding just to emphasize that. So that's one element that's related to 0. So we're asking, what else can you put in here that's related to 0? Whatever you put here also goes there. Next natural element should be 14, right? You could say 21, but let's go in order for the sense of our own sanity, I guess. 14 is the next element. 21 is the next element. If you put 21 here, it's in the relationship R, which is congruence mod 7. Maybe I should say that. R is congruence mod 7, once again. So put 21 here. The equivalence congruence is true. And this is an infinite set, just keeps on going forever in that direction. But notice all we're really doing is, well, really adding 7, right? We go 7 to the right, get an element. So that says, what should be this element going to the left? Would you all agree it should be -7 that does the job? Well, yeah, if you put -7 here, 0 congruent to -7 makes sense because 0 mod 7 is 0. -7 mod 0, it goes in. For some reason, I'm confusing myself on that one. You know, it doesn't hurt to do a really fast review problem. We took, say, -7 mod 7. It goes in evenly. The result is -1. The remainder would be 0. So yeah, I just had to convince myself really hard on that one for some reason. Sorry, I might have done a micro sleep there. So -7 works. -14 works. And so on, going forever to the left. So that's our first equivalence class under this equivalence relation, congruence mod 7. Well, that's 1 down. And again, we would redefine that with a bracket if we were being as strict as possible, knowing the extra structure going on in Z7. We move on to the next equivalence class, this next element. We're rewriting it as an equivalence class with congruence mod 7, which means we're writing down another infinite set. But we can start off in the same way. 1 mod 7 is 1. That means 1 is going to be related to itself through our reflexivity, reflexivity property. The next element would be 8. 8 mod 7 is 1 as well. So that means 8 is related to 1 in that way. 8 is congruent to 1 mod 7. After that is 15. 15 mod 7. Well, that gives us a 1 as well. So we're inside the equivalence class. Same with 22. But notice that there's pretty much a pattern here. We didn't have to put in a whole lot of thought here. Essentially, I just took all these elements, added 1, and that's the right value. If we continue on the pattern going off to the left, say the value that would go here, this one should be a -6. Well, that would imply that -6 mod 7, it had better be exactly 1, right? Let's double check that by hand, just for the sake of reviewing that, because negative modulus has a way of always being tricky. This would be -6 minus the 7 times the floor of -6/7. Let me open up a quick calculator here. Didn't mean to Google it, but here we are. So if we take, say, -6/7, we get that value, but then the floor of that value is going to be a -1 altogether. So this becomes -6 minus 7 times -1. And that does, in fact, result in a 1. So this tells us that -6 is congruent to 1 mod 7. But really all we had to do is add 1. Same idea here. This one would be, oh, forgot the negative sign on that. Let me backtrack. This one would be 13 on the next element here. We had enough space to put 1 more to the left. We would just take this, subtract 7. And so that's pretty much what we're going for the entire pattern. Subtract 7 going to the left, subtract 7 going to the right. On the next equivalence class, strictly just add 1 to all the elements. So if we can do one, we can do, sorry, 5 more, but they go faster once we see what the patterns are. Any questions at all with the first 2 classes? Okay, so here's the last ones. The equivalence class of 2 with respect to the relation congruence mod 7 is an infinite set that goes -12, -5, 2, 16, 23. Verify if you take mod 7 to any single element inside here, you should get 2. So yes, definitely 16 mod 7 is a 2, so that works out. On to the next. Should have made this congruence mod 5, but here we are. We better finish this out. Be weird to give up in the middle. This one will go -11, -4, 3, 10, 17, 24. Now for equivalence class of 4. With respect to that relationship, it goes -10, -3, 4, then 11, 18, 25. And here's the penultimate one, 5. Congruence mod 7 as an equivalence class can now be rewritten as -9, -2, 5, 12, 19, 26. And now congruence class, the equivalence class rather, for 6 is now, here's the last one. So all we're doing is adding 1. This one's -8. This one's -1. 6 goes in. Then 13, 20, 27. Verifying the random last element that we have here, take that mod 7. We'll have 21 for the quotient, remainder is 6. That means it's congruent mod 6. Or excuse me, congruent to 6, mod 7 is the better order statements there. That's all of the equivalence classes. And again, that's how you could rewrite this set. They're true equivalence classes for that algebraic structure, Z7. We had a couple claims. One claim was all of these pairwise sets of equivalence classes are disjoint. So if you try to intersect, say, this one with just another random one, this one right here, they are absolutely disjoint. We're skipping digits from -13 to -9, -6 to -2, 1 to 5. There's no overlap whatsoever with any one of those. And it's the same for every single set we put here. Also, the union of every single one of these equivalence classes results in the original set. So let's write this out. Here are all the equivalence classes. We're taking a union of them now, and this takes a moment, but here's my claim. So equivalence class 4, equivalence class for 5, equivalence class for 6. My claim, that total union is back to Z. And that requires some work to fully justify. We could cite the theorem above that told us that it is a true partition, and then that union is automatic, citing the theorem. But for looking at this on paper, that union looks plausible because look at the order of these. If you go down from this column, it's 0 through 6, restart, 7, 8, 9, 10 through 13, restart, 14s, 15, 16, 19, 20. We're not skipping a single integer there whatsoever. You just keep on restarting each one of these columns, and these sets are unending. So going to the right in that order swipes out all the positive integers. And if we go in this direction, starting from here, reversing the order, go up, we are sweeping through all of the negative integers, not skipping a single one. We didn't have as many columns for the sake of brevity, I suppose. But you can imagine if we had a third negative number here, the pattern would absolutely continue. This number would be negative 15, negative 16, negative 17, and so on, filling out those next elements. So that's effectively what equivalence classes does for us. Any last questions or thoughts, folks, getting through this one? Okay, well, let's take a look into the next relationship R that we're going to take a look into. This one feels quite a bit more abstract. We're swapping out the set A to the set of all propositions in two variables, P and Q, which makes this one kind of a gigantic review problem of logic altogether. We jump back to kind of visualize what they're trying to say when they say propositions in two variables. This is section 3.2 work. A truth assignment for a proposition, much like we're saying here, all propositions, over variables P1 through Pk, sometimes our authors call this atomic propositions, would look something. So we're looking into these kind of propositions, P and Q, P or Q.
Okay, you cut out for like a good 30 seconds. Sorry.
No, good. Thank you for reminding me about that. I got a notification bar probably 25 seconds later. Just to recap, again, sorry about the unstable internet connection. When it says A is a set of all propositions with two variables P and Q, much like what we're talking about the variables here in the truth assignment, and we don't mean propositions like not P, because it involves just the one variable, P itself. We're looking into these kind of propositions, P and Q, P if and only if P, Q, P or Q, and so on. Any proposition, maybe more built up, P and Q implies Q and R, anything along those lines, is going to be inside this set A of propositions in two variables, P and Q. So in other words, A is the set of all propositions that have truth tables that look like these three on the right, but not this one. That's in just one single variable. Then we define the relation just as stacked equality here on the set A by saying P is equivalent to Q if and only if P and Q are logically equivalent. And that's really the same exact definition we're using here for logical equivalence. Logical equivalence would just mean they have exactly identical truth tables. So that's the idea with what's going on with this brand new relationship here. Similar to the last one, which was congruence mod 7, but this time we're saying R is equal to that logical equivalence. Again, that looks funny, but R is just our old notation for a relationship when we had arbitrary ones in definitions typically. Turns out logical equivalence is an equivalence relation on the set A, and you can expand this landscape by adding more variables, P, Q, R, for example. All propositions in three variables, you could expand in that kind of way. As far as the proof goes for this, it goes in three parts just like before. Looks like we won't have time to fully complete this problem. This one is more about equivalence classes, which is effectively one big review problem on logical equivalence in a nutshell. The last part here is kind of a mind bender in a certain sense. It's asking if we look into an equivalence class of any proposition, say the equivalence class of something like this, P and Q. Here's that, well, I don't have P and Q anywhere. If we're looking into equivalence classes like these with logical equivalence, The next thing we can think is all the equivalence classes are telling us is it's the same concept. Much like you could take, say, a PNQ here. If you do a double negation on that, it's logically equivalent to itself. So if we look into the number of all equivalence classes, that number turns out to be 16. The reason it's 16 is because any proposition you put here, it has a truth table and two variables, and there's just 4 rows you fill out for a truth assignment. Every row has 2 possibilities. It's much like the formula for the size of a power set, either include a set or exclude the set. If there's 4 rows, then that means there's 16 possibilities altogether. So what that's telling us now is these equivalence classes, if there's 16 in total, that means there are really 16 things that look like this. We had 3 major ones in this definition: exclusive or, disjunction, conjunction. That's only 3. Then we defined a new one, implication, but that's only 4. We defined yet a new one. The by implication or the biconditional, that's 5 equivalence classes. There's 16 in total, and we use a pretty pared down minimal set, is what this problem is really saying altogether. There are 16 distinct equivalence classes that partition the set of all propositions, and every equivalence class represents the same exact logical truth. So there's a whole lot going on in this problem. I'll complete these notes here if you're curious about what the full write-up is going to look like. But it's a kind of a deeper look into logic. Once you think in terms of ordinary logic, throw a relationship on it, find out it's an equivalence relation. Now we have a profound view of the structure of these kinds of sets as we define them. So it makes it kind of an interesting problem. But for the interest of time, I've used up kind of a lot of time already today. I propose maybe we switch over to reviewing for the final exam instead of filling out this problem here, which will take all the rest of the time to get through part A. But I'll leave it up to the class. Would you rather pursue getting through part A or jumping into the final exam review right away? Anyone have strong opinions one way or another?
I'd like to go into the review if there aren't any other strong opinions.
Okay, thanks for taking the lead on that. I think that's the next logical thing to do. Again, I'm going to come back here after I finish grading on Friday. I'll finish up any review problems that we don't completely finalize on our review, finalizing it on Thursday. And then I'll come back to the 8.4 section and do that last problem as well. For anyone who's curious on how that goes, again, it's a pretty, in my opinion, wild take on logic when you're thinking of what is part C implying. But for the moment, let's save this out. And take a look at the final exam review questions. So my idea with this problem here, or this packet of problems right here, is if you're trying to review these in totality, that's a very, very long study session. So here's where I'm trying to do the impossible and collapsing the whole course into just a representative list of problems. They'll go from the very first section to the last section, not emphasize, not that one, this last section, not emphasizing anything too strongly, just a representative, equally represented set of problems. It goes in the order of the course. Not everything is
Hello?
Hello, sorry about that. My entire Zoom session and the screen share just completely collapsed on me. Us folks here in class were just sort of staring at the screen, hoping it would come back. Yeah, sorry, folks. I think I must have just a very, very unstable connection tonight. This was happening last night as well, so I'm a little bit nervous this computer has an issue. I'm going to talk to the tech people after class is over to see if they can take a look at it, maybe sometime tonight before class on Thursday. But sorry about that for the cutting out on there. Pretty much what I was saying is that this is pretty much just the order of how we covered the course, represented problems. I'll try to give out some hints on what to expect on the final exam as we get through a couple problems. And if we don't get to every single one of them, if you're worried we might skip one that's your favorite problem, for example, don't hesitate to interject and say, hey, Mike, can we do that particular problem first? I'll be happy to skip to it. But again, sorry for the connection cutting out. It's been kind of a rough day here for the internet or whatever's going on, probably a hardware issue as well. For what we have going on in problem one, we're just looking at the basic set operations. So this is kind of a fast problem to start warming up on. Look at set membership and then move into a power set. So I have a pretty basic finite set. This is kind of similar to what we did in lecture notes, homework problems, and exam one as well. U is the alphabet, A through J. A, B, C are particular subsets of that universe U. All we're doing is set operations. B intersects C. This was defined to be the set of all elements X in the universe U such that X is in B and X is in C. So really now that we have the view of the whole course, we can kind of think in terms of really these were just propositions in their own right using logical connectives like the and, or, and so on. So whenever you see intersection, think of the logical conjunction operator, the and. So we're going to take elements in B. Here it is. They have to be also simultaneously the elements of C at the same place at the same time to be in the intersection. So this goes B, checking to the right on every element, no match on B. D, no match for D as well. F has no matches to the right. H, no matches to the right as well. J almost looks like an A, but none of the elements in the set C are equal to the elements in the set B. So if you end the problem like that, that'd be appropriate. The set is empty. Or if you prefer empty set notation, either way you'd like to notate it would be just fine. Usually it'd probably be written out this way. B intersects C is empty on this problem. Well, now we'll move over to the next one. A union B, defined to be the elements in the universe, X and U, such that X is in A or X is in B. So for the union symbol there, think of the logical connective or the conjunction. Conjunction, union, all it's saying is bring things together. So whatever you have in A, just list them out, A, E, I. Then whatever you have in B, list them out as well, but avoid duplicates. If you did put duplicates in your set, I won't be too picky and nickel and dime you on points, but sets are always intended to be written in their most simplest form, which implies no duplicates whatsoever. So go to the set B, write down the elements, B, D, F, H, J. Doesn't look like there's any duplicates. The intersection between A and B is empty as well. So that would be the entire union. Next, we're going to go to this, the complement of a set, and then set minus. But any questions with the first two basic ones? Okay, let's take a look into the review for the complement of a set. There's a lot of notations for the complement of a set. So if you wrote this out in a different way when you're studying, no harm done. The official notation from our textbook is the squiggly line. But when you see that squiggly line, think not. It's defined in this way. It's the X set of all elements in the set U, the universe, such that X is not in C. Really, this implies a partition. The partitions would be C and the complement of C. So we just go take a look at what C is, delete them from the set U, but write everything else. So let me do just a temporary mark. If element A is here, delete it. Element C gets deleted as well. E is gone. G is gone. And so is I. All of the survivors are the elements in U that are not in C. So write in B, D, F, H. So that's our entire set complement. So if we take C, union, the complement, we just get back the original universe. So that's 2 down, kind of relaxing problems compared to some of the work we've done in this course. Last one is going to be set minus, but again, the major defining feature of the complement of the set is not an element of, a kind of negation. So now for set minus, the way we defined set minus was we said A set minus C feels kind of similar in this sense, except it has a different universe when we go to write out the first part. A set minus C is going to be the set of all X in A. Let me see if I can write this slightly more parallel. Such that X is not in C. So all we're taking out is any element that happens to be in the set A that's also in the set Z. So going back to those two sets, here's A. Any element that's in C, we take out. So we have to set minus that entry because it's in the set C. I is also in the set C, so we take that out. Hey, A is also there, so we take that out. Or I slashed it out in the wrong order, take that out as well. So A is contained in C. If we set minus C, there are no X's in A any longer that have this condition being untrue. So this means this one comes out as the empty set as well. Well, that's a quick set of the tour of all these operations. Again, think of the set minus, sometimes a trickier definition, but all we're really thinking of is A takes the place of the universe, and it's kind of a type of complement that we're really doing relative to a brand new universe, just the small world of A itself. Next, we're looking into subsetting relationships. And I think we have enough time to write down a definition. We can say that A subset equals to C means for all X in the set A, X is also an element of the set C. So in terms of a universal quantifier, that's all the subset membership condition means. It's subset equals to allow for both A and C to potentially be the same exact set. Usually the way I think of this visually is it's containment. In Venn diagrams, A is inside C itself. So if we look at A, it's AEI is in there. Or if we look at the prior problem, the fact that we got the empty set confirms this as well. Every element in the set A is in fact in the set C. We can confirm it visually. So this means A subset equals C, I'll just say usually subset for short, is true. Then same idea, B subset C, let's double check that before we make a determination. It has, we can look at that first part. When we intersected B and C, they had nothing in common. But even if we didn't look at that first line, B is inside this set. It's not inside the set C whatsoever. So that breaks the universal quantifier here. So we can say B subset C false. And the falseness is because Well, if it's false, that means we're negating this whole thing, but it's false because there exists an element X and B such that X, negate this part, is not an element of C. You don't have to write down the quantifier part, but as an exam review, it's kind of a good idea to tie these concepts together. Almost everything we've done in this course, including relations, can be viewed through the lens of quantifiers in some way. But last one, effectively just a trick question, is that this relationship is always true. The empty set is a subset of B vacuously. So that is vacuously true. And sorry, it looks like I read over a half a minute, didn't intend to do that. But when we come back on the next class, we'll run through the power set, see how that goes, start reviewing logic, and possibly cherry pick on certain problems at the very end to make sure we hit everything interesting you'd like to see reviewed. But sorry for running over by a minute so far. Any last questions or thoughts, folks, before we call it a day?
I just want to check. We've been for B, we've had that full subset, I think. If we didn't have that line at the bottom of that symbol, I can't remember the symbol, would it just mean that for some X in B, there's an X in C?
It would still mean all of them have to be. So if you wrote B subset C, this version means for all X and B, we have two conditions. We have to have X in C and B itself is not equal to C as well. So, you know, this one probably could be written better as nested quantifiers. Every element in B has to be in C. However, there must exist some element in one set or the other that's not in the opposite set. So if we take off that bar there, all we're saying is we still have containment. So they're still for all, but we're not saying the sets are identical. They have to be unequal sets.
Okay.
Other questions at the moment? Okay, well, have a great afternoon, folks. I hope the reviewing is going well for the other courses. We'll be back to this on Thursday. And if there's any particular problem you'd like to see solved, even not on these notes, don't hesitate to ask about it. Start a class over email. Otherwise, I'll always be happy to start with your questions. But have a great afternoon, folks. We'll be back to it on Thursday. Awesome, thanks.
I have, or I don't know. I did this one way originally, and then I realized there's a simpler way.
Oh, cool.
I'm not sure. I was kind of interested what you think of this.
Anti-symmetric? Yeah.
Yeah.
So let XY be in the relationship. Assume that XY is in R. And this relationship was,
That was y cubed is less than.
okay, gotcha. So I guess I could have just wrote it from here to here, yeah.
X cubed less.
So x cubed less than y cubed. So case one, assume, that's a great way to go by cases because there's two possibilities, either equality or strict. So if x cubed is strictly less than y cubed, then y cubed would be larger than x cubed, so that relationship is false, not in R. Yeah, I like that case. And then likewise, case two, assume x cubed is equal to y cubed. So if x cubed is less than equal to y cubed, or x cubed is equal to y cubed, switch this around. X, y, and R, x is equal to y by assumption here. Applies x equals y, so anti-symmetric. Let me think about that. Yeah, because it's odds, I think that this here does imply X has to be equal to Y, but sorry, I interrupted you on that.
I don't know. I just feel like there might have been a logical jump somewhere, but I can't like see where, you know,
Yeah,
that's,
let me track through again. So that's equal to that. We're trying to switch the order here to get YX. Y cubed less than or equal to X cubed is true, and X equals Y. So YX and R only when X equals Y. So yeah, that kind of flows here, but once we wrote that statement, we got that result. No, I don't see any issues with it. I kind of like it.
Hmm.
Let me read the shorter proof. So X, Y, and R, assume X and Y are related, and then Y and X are related. Then X cubed is less than or equal to Y cubed. Y cubed is less than or equal to X cubed, which absolutely implies X must be equal to Y, anti-symmetric. Yeah, I like the way you went here. I agree with that one. For this one, I'll take a closer look at it, but from what I see so far, I don't think I would have had complaints if you left it just like that.
Mhm.
Let me take another quick look. So we have X, Y, R, we're assuming that X is related to Y. So this is the overall assumption. But now in the new case, we're assuming that they're the same, which then is true. You could switch the order. Y cubed, it would then be less than or equal to X cubed, which would satisfy the relationship. It's then an R. The and really flows from really just this. If
Yeah,
X cubed equals Y cubed, it really gives us the X equals Y. So yeah, I see what you mean by the logical jump.
Mhm.
So X cubed less than Y in case one kind of goes back. So if we Y, X, and R only when X equals Y kind of uses this information here, because if this case is true, X is not Y. If this case is true, X equals Y, and it's in the relationship. So I think it flows okay. I think it's got all the right elements. So yeah, it definitely works as a proof on that one. I don't have any specific complaints that I can come up with on it. But other questions about it so far? Gotcha. And yeah, I know what you mean. This one looks slick after thinking in terms of that kind of approach here. This one
Yeah.
works just as well.
Yeah, I looked at the in-class stuff after that and realized this is a lot
Mhm.
better.
It was kind of a similar comment that you made as well, where I think we proved anti-symmetry, then we made another proof of asymmetry, but you cited the same argument that we used on anti-symmetry derives the property of asymmetry at the same exact time.
Mhm.
So same kind of idea.
Yeah, for the words, like symmetric,
Mm-hmm.
anti-symmetric, and asymmetric, if it's none of the above, would we call it non-symmetric or?
You know, I think that's usually avoided because the negation of symmetric or the negation of anti-symmetric, the negation of asymmetric, any one of those could still be a symmetric set. Well, let me think about that further. The negation of symmetry could still be anti-symmetric, asymmetric. I think the only reason we usually avoid that is because you can write a relationship that has one of the three, two of the three, any two of the three, all three. And we never really touched on this, but you can also write a relationship that has every single property all at once. Because one of the things that was kind of glossed over is the relationship being a subset of the cross product actually allows it for to be the empty subset. All the properties can now flow from vacuous truths now. So one relationship, the empty relationship, the silly one, has every property that's on paper: symmetry, reflexivity, irreflexivity, transitivity. So I think that's the only reason that they typically don't use those kind of words to say none of the above. We say it's just not symmetric. They usually just say verbatim does not have any one of those specific properties.
Okay. Cool. Well, I'll see you.
Yep, take care.